Okay, so today we'll have a material that is sort of going slightly beyond the kind of like standard canvas of this course. We're going to branch just a little bit into path planning, or cover a little bit of the material related to how to plan a path on discrete sets, or on graphs, I guess. The reason I include this is twofold. One is this can be done as a convex optimization, which is kind of the core idea of this course, was to do things that are can be done very effectively with convex optimization. That was one of the things. Another one is, historically, this type of problems have been a backbone of robotics. And if if you, for example, look at something like Asimo robot, one of those first big breakthroughs of robotics into mainstream attention. I mean, robot arms, for example, were a big industrial breakthrough, but Asimo, I think, have been a breakthrough in the kind of public attention. It was powered by A-star algorithm. So the search it was doing it with A-star. So in a sense, this important algorithm. An A-star is well seated today, is one of the methods for that can be used for planning a shortest path on a graph with weights. So in a sense, there are historical connections. Right, but for us, what is interesting is the fact that some of it can be done as a convex optimization. But we'll see a start. Okay, let's look at what this is all about. So, shortest path on a graph is an idea that you can find the path through on a graph that is, basically a graph where each edge has associated weight with it, right? So each edge has a weight associated, and we can try to find the path from, let's say, a initial point. Let's say initial point is somewhere here, just as an example. Let's say the goal point is somewhere here, again, just as an example. Okay. We can find a path that connects those two. Like arbitrary path can be maybe something like this and something like that. I apologize for drawing not very well. As the last few classes I've been using touchpad to draw. So I apologize. But you can imagine the connection can look something like this, maybe, right? And here we have a path. Okay, so is it the shortest one? Who knows? But you can definitely imagine taking a longer path. For example, if I went somewhere here, let's say here, 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 here. Let's just say here. This segment would only increase the length of the path. It's not going to, visually at least, it's not going to do anything good. So this is a problem of finding the shortest path from one node to another node. How is it relevant to robotics? The relevance is kind of like this. Let's say you have a car that has to drive from a point A to point B on a map. Ideally, you would want to be able to get a route from point A to point B, but how do you do it? Well, you can imagine representing certain points on the map as nodes, connection between those points as edges, and then you can say, okay, let me try to plan a path from point A to point B. That is one possibility. Another possibility is, let's say, is just like how you can theoretically do it. Of course, in the city, there is a lot of work already done, how to plan paths through the city. You probably know how easily apps can do that for you now, and you can look up what algorithms they use. But you can also imagine that it's not necessarily just a city. It can be inside for example, it can be a robot with wheels that operates inside the warehouse, and the warehouse may be, with obstacles that appear and disappear, and each time you have to replan and so on. So that is an application. Another one is, let's say you have a drone and you want to plan your path through a cluttered environment. Another one is you have a end effector of your robot and you want to plan a path on let's say, like through a few obstacles that exist in your workspace, and so on and so forth. All of those require some simplifications. Like, for example, for the robot arm, it is unclear how you're going to take into account the fact that the end effector is connected to the other parts of the robot arm, right? With the car, you have to take into account the fact that you have to turn, and you have to have enough space to turn. And if you have traffic rules, you have to account those, etc. So each time you have some limitations. But ultimately, especially for bigger distances where geometry plays less and less role, you can easily imagine this being a problem that you could try to use, try to formulate. All right, all right. So the problem is how to find the shortest path on a graph, and that has been used in robotics extensively. It has been used in the 90s, and it is still being used now. So it's not a historical artifact. It's a modern tool. Okay. Now, let's consider directed graph. Directed graph means that we have like each node has a direction. Okay. We'll consider one of the points as a goal point. Let's say this is a goal point. Okay. And we'll consider one of the points as a starting point. Let's say this is a starting point. Okay, so we go from starting point to the goal point. Directed graph implies that you can only go in the direction that the arrow shows. So you can only go this way, and here you can only go this way, you can only go this way, here you can only go this way, and so on, right? Or this way, you cannot kind of go against the direction. If you don't like this fact that it is directed, like for example, you say, oh, I want to go backwards and forwards. Well, it's very simple how to amend this. In order to amend this, you just introduce additional sets of arrows. So you make two connections between two nodes, and another connection would go something like this. So add second set of connections. Okay. And this preserves your directedness. So you still have a directed graph. It is just that neighboring nodes would have two connections between each other. That is how I see it. You would need to verify that the math works well with this. So I didn't verify it. So, but I don't see at least initially, I don't see any problems with this. All right. So you would have this kind of situation. If you want to be able to go in both directions, directed graph shouldn't present you a huge problem. Okay, now the question is how to find the shortest path from node to finish. Well, first of all, we will have a cost associated with each of the edges. Each of the edges. Let's say the cost here is 2. The cost from traveling from A to B is 2. Okay. Let's say the cost of traveling from B to C is 5. Okay. Let's say the cost of traveling from B to D is 7. Let's say the cost from traveling from C to E is 1, etc. Or we can give those costs the way we want, and it would, somehow inform what is the shortest path. So we don't kind of eyeball the shortest path. We need to compute it. So, for example, traveling In this direction gives us, for example, traveling by this route. Let me just demonstrate the route. Traveling in this route from here to here, from here to here. Let me try to add arrow that would allow me to travel actually this way. Okay, so traveling from here to here, from here to here, from here to here, and from here to here would give me the cost of 2 plus 7 plus 2 plus 7. Okay, so it would be 18, right? Traveling this way, on the other hand, let me use different colors so it would not blend in completely. So traveling this way, green path, would give me 2 plus 5 plus 1 plus 7. So 15. Okay. So you clearly see green is a better path than red one. They look kind of the same, but the cost is smaller for the green one in this case. So the question is how to find a path like this. Not obvious. Not obvious. All right. Now I will just give you algorithm. I will just give you algorithm. I'm not going to prove it. I will just going to give it to you. The algorithm is going to be based on LP, but yeah. All right. So we assign index variables x sub I to each edge. So x sub I would be ith edge. So not to node, but to edge. Okay. Each index variable is positive. Okay. So if the index variable is equal to one, then the edge is part of the path. So if the index variable is one, we'll assume that this edge is traveled. Right? And by the way, I also assume that each edge is going to be only traveled once. We don't allow loops, which yeah, is kind of interesting. But it sort of makes sense. Like shortest path shouldn't contain loops. So if xi is 1, then it is part of the path. We assume that otherwise it will be xi it will be equal to 0. This is kind of interesting. Those variables, they're not binary. They're integer. They're real variables. But we just are going to encode this whole problem in such a way that we will treat them as if they would only be expected to contain values of 1 or 0. But they are real variables. They're not integer variables or binary variables. All right. Now, we have this cost d that I was playing around on the last slide, associated with this edge, with each edge. So and since each edge has xi variable associated with it, the cost is also associated with each variable. So we can get a linear cost very easily. That would look like this. So x times d. Okay. That will x times d means x1 times d1 plus x2 times d2 plus x3 times d3, etc. Since the edge on the path gives us the value of x equal to 1, that means that associated cost will be added to the cost function. If the edge is not on the path, then I will be equal to 0, and 0 times associated cost will be 0 still. So the cost for the edge which is not on the path would be 0. So that means that our linear cost will only contribute to the, would only increase with the edges that are on the path. Okay, so that is how we deal with the cost. Cost is linear, and we expect only the edges that are on the path to contribute to the final cost. Okay. Do you have questions here? Do you have questions here? Okay, interrupt me as soon as you want to ask something. Don't wait for me to pause. Okay. This might be a little bit complicated. Since each edge connects one node, okay, so for example, node U to another node, for example, node B, okay, we can denote each of those variables with a superscript. Okay, so x u v. So x u v just means the x that connects u to v. Okay, that is just a convenient notation. It's going to be simplify our life a whole lot. Instead of saying x2, which connects node number 7 to node number 31, we say x superscript 7 31. So clear. How to map the superscripts to the subscripts? Well, that is a separate question. We can just make a table somewhere. It doesn't matter. But notationally, this is very easy. Okay, so our goal will be to count how many path segments enter and leave each node. Okay, we're going to count how many path segments enter and leave a node. So for a normal node, which is not a goal node or a starting node, the number of path segments that enter it and the number of path segments that leave it will be equal to one another. That is quite interesting. So we have, so for all I, for all means, so what does this notation mean? Let's try to understand this. 1 second, I'll just take something to show. What does this notation mean here? Well, it means path segments which lead to node V, okay, lead to node V from any node I, okay, so from any node I. So this is the sum of all path segments that lead to node V, okay, and this is a notation that implies all path segments that lead out of node V to any node G, okay, J, right? In any node J. So we have this sum here and this sum here. So we assume that the nodes that lead into the path segments that lead into the node have a minus sign. The path segments that lead out of the node are plus sign. Notice that if the path segment is active, so it is a part of the actual path that we are constructing, then it will be equal to 1. If this path segment node is not active, so it's not actually part, so if the edge is not active, it's not part of the path, then it will be 0, so it would not influence the sum in any way. So the only parts that are of interest here are the parts that are actually part of the path. So the number of connections that go into the node, let me draw it, I guess. Here's a node. Here it has a ton of connections that lead into it, okay? So 1 connection, 2 connection number 3, connection number 4. So a lot of connections. And let's say it has only 2 connections that lead out. That doesn't matter. That signifies absolutely nothing, how many connections lead in and out of the node. What is important is that there is a 1 path segment that lead into the node and 1 path segment that lead out of the node. That is one option. Another option is that there are 0 path segments that lead into the node and 0 path segments that lead out of the node. Okay. Theoretically speaking, you could also have like another path segment that leads here into the node, another path segment that leads out, but that is unlikely because it's not going to be shortest path if you have a loop. So the only 2 scenarios for a regular node are either you have 1 connection in, 1 connection out, or 0 connection in, 0 connections out, if you only count parts of the path, not all connections, okay? And all other connections will be just set to 0, so they won't influence the sum. So essentially, you just sum all the path segments in, all the path segments out, and the sum should be equal to 0. Okay, that's important. You can think of this as a hyperplane with the coefficients like this, a linear equality constraint, and the coefficients of this linear equality constraints are all 1s or -1s. So you can imagine graphically, if it was like a 2D case, that's kind of interesting. If it was a 2D case, what would it be? Let's say you have 2 variables, x1, x2, and you say minus x1 should be equal to x2, right? Minus x1 should be equal to x2. So the graph in this case would look something like this, I mentioned, right? Is that correct? minus x1 equals to x2, minus x1 equals to x2. So it is a diagonal line with the that lies in the middle of a quadrant. Yeah, and it looks like this. So this is was of course in the high dimensions it would be like a hyperplane, but the point is it still kind of looks like this. Okay. And all for all nodes, we add this constraint. So this constraint is added for all possible nodes. So each node we test for it this constraint. So if the graph is big, we're going to have a lot of constraints. Okay, good. Now, for a starting node, this becomes a little bit different. For a starting node, we say that the sum should be equal to 1. So because positive numbers come from the path segments that leave. Okay, positive numbers come from the path segments that leave the node. So this is for all j nodes. So all path segments that go from the node S to some other node J. And those should prevail over the path segments that come from the nodes outside that try to enter the node S. And the prevalence should be by 1. Why? Well, because ultimately what we expect in this case is that we would only have one path segment that is going to leave. Right? Well, what we expect is actually this situation. We expect the node, and there will be only one path segment that would leave the node. There can be other connections, but a path segment should only be single. So there could be other connections to other nodes, doesn't matter. Could also be connections from the outside, again, doesn't matter. What we expect is that there will be only one path segment that leaves this node. You can ask me if this makes sense to write it so complicatedly. Why not just to write that this, for example, is equal to 0? Like say this, the sum of all those things should be equal to 0. You can also say the sum of this and have to be equal to 1, etc. I mean, not going to try to answer. Looks sensible, but you have to prove that it will give you good results. And I'm giving you now the version for which you would have proofs. But yeah, you can think of it. Why do you need this part here? All right, for the final node, you have the same exact situation, but now you have -1 as a sum. So the parts which are entering it, so from the node number I to the final node, for all kinds of nodes number I to the final node F, you have to have one more path segment entering the final node, as opposed to the number of segments that leave it. And again, what we actually expect is that there will be a single path segment that enters final node, and that is, and since they come with a minus sign, you'll get a -1 there. Again, you can ask yourself, why don't we get rid of this, for example, right? Say there is no path segments that leave the goal, and this should be equal to 1. You know, think about it. You can read the proofs. I'm going to discuss it. So, but I apologize. I'm not going to discuss it because I'm not prepared to discuss it. Of course, not because it is not worth discussing. But this is how we think of those things. Okay. This is how we think of those things. So for two nodes, final and static, we have conditions that are slightly different. The difference is only in those two numbers. So here is 0, here is 1 and -1. Okay. And you can imagine how nice it is. You can just do same exact style of constraints for each node, starting, middle, finish, doesn't matter, for all of them. And then you just put 1 and -1 to indicate starting, finish node, and you get your like and you know, that's all. That's all you need to indicate that they are starting and finish node. So essentially, this is kind of nice. You can always re-indicate your starting finish node by just changing this right-hand side. So maybe that is a good enough reason to stick with the uniformity, right? Okay. Now together, all of this gives us this linear program. Linear program. Here's our costs that we discussed previously. Here's our constraints on intermediate points. So everything except goal and start. Here is our starting point. Here is our goal point constraint. And as I said before, importantly, all x's should be positive. That problem is LP, and you can clearly see that it is very easy to solve it. Now, there is a proof that I'm again skipping, that the solution is going to give you only zeros and ones. Now, why does it give you, so how do we interpret it? First of all, it is LP, linear problem. So since it is LP, we can instantly reason something about it. So first of all, what we can reason is that there is, like, you know, if it's how should I put it? A domain looks, let's say, like a box. Like if it looks like a box, then the solution would have to be, since it is LP, the solution would have to be on the edge, on the vertex, sorry, on the vertex. So here, or maybe here, somewhere on the one of the vertices. Solution cannot be anywhere else. Why? Well, because it has linear cost. So if it strikes the boundary, let's say a face or an edge of this box, unless the face or edge is orthogonal to the direction in which x decreases, which means that edge or a face is orthogonal to vector d, which is statistically improbable. Practically, of course, perfectly possible, but statistically, the chance is zero. So unless this happens, you would slide across the edge to the vertex, and that is how you end up at the vertex. So your solution to NLP would lie at the vertex, unless it is degenerate constraint of some kind, like unless there's some kind of singularity. Okay, so nice, good. This is how we prove that the solution lies at the vertex. We know something about this particular vertex here. So this particular vertex, let me show you. Here is a point 0, 0, 0. How do I know? Well, because of this constraint here, we know that all x's are bigger or equal to 0. So there is indeed this kind of like a this shape where we cut off half spaces associated with negative x1, negative x2, negative x3, and it will be kind of like a righted corner. So it will be what we call a cone of positive numbers, right? So it will be just basically a quadrant, like a first quadrant, we can say, but in high dimensional space. Is a domain of this constraint. Okay. And here we know that it is going to be 0, 0, 0, 0, this point. Okay. Good. That is one thing that we know. Now, if only we can somehow prove that the box does not reach higher than 1 in any direction, then we proved the situation. So somehow, in order to prove that the solution will be either 0 or 1, we just need to prove that the size of this box, each side of this box is the size 1. So, and for this, you would have to use those constraints to prove it. And, you can see that maybe in order to prove it, you would have to somehow use those two numbers and maybe some properties of the graphs. But I'm not going to attempt to prove it. But I'm just saying that in order to, you shouldn't be surprised that the result is x as a result is either 0 or 1, because a result of LP is always at the vertex of a domain. The domain here is unclear how it looks, but if we can somehow prove that it looks like a box, which I'm not sure if we'll be able to prove. I don't think we would, but if we could, then we would be satisfied instantly. Of course, what we actually have is a half space, so we have just half spaces, and we have just a quadrant in a high dimensional space, and a ton of linear inequalities here that kind of slice through it. So we would have to somehow use those to argue our case. All right. That is it. That's what I wanted to show you here. The important part here is that you can solve the problem. Apologies. Clear all. Clear all. Okay. So the important part is that you can solve this problem, right, as an LP. So as a linear program, and linear programs are the most efficient, fast, etc. So you can expect rapid solutions. So that's very efficient. The minus is that you have to have a directed graph, not just any graph, directed graph. Okay, now the code for this can look very simple. That's the MATLAB code again. We have 5 nodes. We generate them randomly. I give each of them coordinate on 2D space in order to generate a cost of traveling from one node to another. So here's the connectivity. So we say that the first node is connected to the second node, that is H1. First connected to the third, H2. Second connected to the third, H3. Second connected to the fourth, that's H number 4. Node number 3 connected to node number 5, H5. And node number 4 connected to node number 5, that is H6. Now, here's the cost. Here is the number of edges. Now, how do we compute cost? Well, for each edge, we just find the distance between positions of those nodes in Euclidean plane. Here we just use this to generate those positions. Now, here is the optimization problem, the way it looks in CVX. So we create variables. Is the scalar variable 1 for each edge. We have 6 edges, so we have 6 scalar variables. We have a dot product between D and X. Here we say that X is all positive. Here's the condition that the node number 1 would be the starting node. Here we starting node, right? Here we'll have a condition that node number 5 is the finishing node. Let me just verify that I'm not saying anything. Yeah. Okay, the finishing node. And here we have conditions for all other nodes. Remember, we have 6 edges, but 5 nodes. That is why we have 2 conditions for start and finish node, and only 3 conditions for remaining nodes. So conditions for node number 1, number 5, number 2, number 3, number 4. That's it. That program is going to solve you for the optimality. Do you have questions now? Do you have questions?
I just have one small question.
Yeah, go ahead.
So how does this method, for example, compares to other known, like, for example, for me, when I have like a graph problem, I would think about like Kestra or A star or like these known algorithms. So is this one faster? Like,
yeah, good question, right? Comparing with A star is a little like we'll see a segment on A star in just a second, so I will be able to. It'll be easier for me to a little bit to explain, what's going on. But ultimately, the problem with this algorithm is that as long as the program is small, it is very fast. But very fast is still relative to what? Like faster than other types of convex optimization for sure. But faster than A star? Good question. It would depend on what solver you use. If you're going to use a very good solver, especially LP solver that is specialized for fast solutions, then you can expect a very good performance. If you're going to use like CVX, for example, which would call very likely something like Sedumi or Gurobi to solve it, the overhead on creating the problem plus the solving the problem can already be significant. Plus, here you can imagine if you have a ton of nodes, let's say you have 100 nodes, you're going to have 100 linear inequalities. That is not a lot. That is a very small number. So no problem at all. But if you have fully connected 100 nodes, so each node is connected to each other one, that is, by the way, completely unlikely. You never have fully connected graphs in this type of problem. I mean, if they're fully connected, then the goal is connected to the start. So trivial problem actually. But if it is fully connected, then you would have 10,000 connections, and you would have 10,000 variables. And that is a little bit of a problem. 10,000 variables is not unsolvable, but it is going to take a little bit of time to solve. So it's not very good. It's not very good. Now, typically what you would have is, for example, let's say each node would connect to 8 neighbors. 8 neighbors. So 8 connections for each node. Plus, if you're going to have double connections to account for one-way traffic on each connection, then you might have even 16 connections. Well, let's say 8. Let's say 8 connections. For 100 nodes, and 100 nodes for a 10 by 10 grid, that is, so your whole map is 10 by 10, so not very fine grid at all. You would have already, 800 variables? A lot of variables. So this algorithm can grow in number of variables very fast, and that might not be what you are happy with. So that is a bit of a problem. That is a bit of a problem. Whereas A star doesn't care as much. However, with A star, the problem is to allocate memory, not allocate memory even, but use algorithm that is makes it easy for you to access this sorted kind of like a array of best guesses for the next node to add to the path. Okay, and if you are going to use a very good algorithm, it's going to be extremely efficient and most likely will beat this one. Most likely will beat this one. Yeah, so there is that. There is that. But you have to be accurate when using it. But A star doesn't allow you to optimize anything. And A star requires a heuristic. This one doesn't require a heuristic. So if you don't have a heuristic, you don't have an option to use A star. Okay. And if your heuristic is wrong, somehow it, for example, overestimates the distance at these ones, you're not even guaranteed to have a shortest path with A star. And you in A star you cannot get additional constraints, etc., which this algorithm like with additional work, of course, will allow you to do. So two different beasts. You should know both of them. All right, hope I answered
Thank you. Thank you. Yes, you did.
All right, well, since we start talking about A star, let me just introduce it, what A star is. So A star is a different popular shortest path planning method on a graph. We denote it sometimes as A asterisk, so A star. So this doesn't involve convex optimization, but it involves a heuristic. Okay, heuristic is again like a guesstimation. Okay, we'll again have to consider a graph whose edges have cost associated with them. Here, directedness of the graph doesn't play a role, so we don't care about directedness of the graph. Now, here we'll start slowly understanding this terminology. So let P be a node on the graph that the program found a path to. Okay, so we know the path to P. Okay. So that means that we have a predecessor point A of P. Okay, A of P. You can say A stands for ancestor. Predecessor and previous, etc., all starts with P, and you know, I decided to use A, ancestor. Okay, predecessor point A of P. That is the last node in the path towards P. Okay, last node in the path towards P. Okay, so since each predecessor knows its own predecessor, so for each predecessor of P, you have its own predecessor, so it's kind of like matryoshka doll. They know what comes before, and their predecessor knows what comes before, etc. We can recursively construct the path from P to the start. And all we need to know is the previous point in the path. So we have P, and to reconstruct the path, we just ask P, what is your previous point, previous node? It tells us. We go to that previous node, we ask it what is its previous node. It tells us, and we go towards the start. Of course, if we found a loop, we could be endlessly in the loop, but that's not going to happen because we constructed them from the start. So loops are not going to happen here. All right, that is the first aspect of the problem. Second, if we found the path from the start to P, we can construct a sequence of edges that we travel to get to P. So to get to P, we construct a sequence of edges. So we go through the edge E1, E2, En. Okay. And for each edge, we have associated cost. So each edge has a cost. The cost would be C1, C2, Cn. Okay. So the total cost for reaching P, we denote it as G of P, the cost of reaching P. And this is just the sum of those costs associated with each edge that we traveled to get there. So that is the total cost. Okay, good. Now, we also have a heuristic H of P that is, while being kind of accurate, always underestimates the cost of reaching the goal from the node P. Okay. So a heuristic gives us an estimation of how much it will cost from the point P to reach the goal, but it always underestimates. Okay, that's the important part. Now, if we have this, now we can do A star. So A star is just surprisingly easy in this case. We say that the next point P, so the next point P in the that we're going to consider is a P for which we can find the smallest possible cost and smallest possible heuristic. We only consider the points which we can reach with one step. Okay. So let's say we have like 10 points that we explored, and from which each of those points we can go somewhere into unexplored points. If the point was previously explored, we are not going to consider it because we already have a shortest path to the point. No reason to merge another branch into it. So let's say we have like 10 points, and for each of them we can go somewhere else. So we have, let's say, 20 candidate points that we can add to our consideration. Okay, 20 more points to add. Which point are we going to add? Well, in each of those 20 points, we're going to compute the cost of reaching those points, which is quite simple. We'll see how it's done on the next slide, but ultimately you can see if we have a point which we can reach from a point P, we compute the cost of reaching point P and add to it the cost of going across the edge to that new point. Okay, so quite easy. And the heuristic just works for each point. So we just apply the heuristic and say, oh, how much is this? Like this new points that we're trying to add, what is the value for this point? And out of those 20 points, we compute for each of them this function, and we find the ones that gives us a minimum of this function, and we just add it to the list of consideration. Okay. Next, we will have 21 points, and we will consider all the points that we can reach from each of those 21 points. So that is how the algorithm works. Eventually, the points that we're going to add is going to be a goal point. And if it is a goal point, then we reached the shortest path. So as soon as we reach the goal point through this process, we know that we found the shortest path. Okay. Okay. Now, in practice, G of P is not computed like this. Okay, we're not going to unwind all the path and compute this. Doesn't make any sense. Instead, when we get our next point that we want to, for which we want to compute G of P, we find its predecessor P of A, and we find the cost associated with the edge connecting P of A to P next. And that will be C of A. CA. Okay. And then we assign the value of G of P next. So we can assign the value of this function. We don't have to compute it each time. We can just store it in memory. And that will be equal to G of P next is equal to G of P sub A. So the predecessor cost plus CA. That's it. And we just store this in memory. Now, heuristic might be difficult to formulate. But for example, if we have each point associated with the coordinates on the Euclidean plane, then we can use Euclidean distances as a heuristic. So Euclidean distance to the goal is a heuristic that you're using. And the Euclidean distance can be used as a heuristic for your edge costs. All right. All right. Now, a grid can be easily become a graph. So for a grid, you can say your connections could be something like this. This one is, let me use a smaller font. 1 second. So you can say this node is connected to this node is connected to this node, and this node is connected to this node. You can say that this node is connected to this node, to this node, to this node, to this node, and to this node, etc. Right? So you can easily use grid to replace a graph. And you don't have to have an explicit graph-like representation of your whole thing. You can just use this grid and say, okay, let me find what are the adjacent cells in the grid to the cells that I already explored. Let's say you explored cells, I will denote them in orange. Let's say those are your explored cells. Okay, those are, let's say, your explored cells. Let's say maybe even this one, maybe even this one. Okay, what are adjacent cells? I will denote them in green. You'll find this is adjacent and not explored. This is adjacent, not explored. This is adjacent, not explored. This is adjacent, not explored. This 3 also adjacent and not explored. So you get, in this case, 6 cells that are adjacent and not explored. For each of them, you will evaluate the cost to get there and the cost heuristic. And you would, as you can guess, the cell that is going to get your best heuristic is going to be here, because this one is closest to the goal. Okay, and cost to get, but in terms of cost to get to, the best cell would be this one. The best cell would be this one. Yeah, the best one is this one. But in here you would have to wonder if this huge value of the heuristic will overwhelm the difference in cost. You'd have to wonder what will override the difference in cost or a difference in or a difference in heuristic. All right, so that is how A star works. Of course, if you're going to implement it, do read additionally on it. That's kind of just overview. And also there is a lot of implementation. Implementation of A star is much less about what I just told you here and much more about memory management. You have to store all of this in memory. And important part is to make sure that you can retrieve your best guess very rapidly. So often enough, what you want to do is do some sorting or whatever to make sure that your best next candidate it does not require going through all the candidates before it when you are going to edit. Like for example, a heuristic for each cells that you that are adjacent and unexplored is not going to change. So there is no reason to evaluate it again and again and again. You can just store it. Same for the smallest distance, like the distance for all those cells is also not going to change. So you can store all this information in memory. And when you find new unexplored cells, you can, for example, add them in such a way that the whole method, the whole thing is sorted, and you will always find the next best candidate at the top of the queue. So this kind of thing. Of course, again, here you have to, if you're going to insert something somewhere, etc., you need to make sure that you don't create memory overflow or anything like that. Like you don't want to, for example, reallocate memory each time you add a new element. If you're going to have thousands of elements, allocation of memory will become a problem. So you would want to create some sort of structure that doesn't involve memory allocation in unnecessary amounts, etc. So what I'm trying to say is the programming part of implementing this, computational cost management, is the key. And you shouldn't look down on this. You should absolutely either use ready software or study carefully how people implement this. This is kind of like sorting. If you're going to have sorting in your program, unless it is a trivial case, you better implement it well. Or use something that is already implemented, but you shouldn't kind of like just do it badly and leave it as it is and waste a ton of computational power. Same here. Same here. That is a big advantage of previous algorithm, where you don't have to think about those things. You have to think about which solver you're going to use, etc. While here you have to do this hardcore programming kind of stuff. Okay. I think that is all that I wanted to say for today. That is all. Do we have questions?
Yes, Prof.
Yeah, let's go ahead.
We can solve the last problem using dynamic programming.
Dynamic programming.
Yes. So
Yes,
what advantage A stars give us over a dynamic programming?
Dynamic programming, if you're going to use it here, is going to, and here I'm going a little bit from memory, but it's going to explore all possible nodes. So instead of just going straight from the goal to the finish, it's going to go from the finish to all possible points, as far as I know. And this whole grid is going to get its cost to go after your dynamic programming run is done. Maybe I'm wrong. Been a while since I played this dynamic programming. So the computational cost for dynamic programming, I would imagine, be much higher. A star is just a way to quickly go to the goal when you already have a inclination how to get there, and that is a heuristic. What heuristic does, it gives you the idea how to get to the goal faster. Well, dynamic programming doesn't involve any such thing. It doesn't involve getting some heuristic. It just goes from the goal to each point, including the start point. And once you solve dynamic programming, you can resolve it from any initial condition. So you can instantly get the optimal path from each initial condition, as far as I remember. So it is much more computationally expensive procedure, but it is kind of like LQR. It gives you optimal solution from each initial condition once you solve it. I hope I give a correct answer. Again, it's
Okay,
like
thank you.
and okay. No, thank you for the question. Any other question? All right. I think that is it for today. Let me stop the recording and we'll just spend 5 minutes discussing the rest of the course.